Hello and welcome to my YouTube channel. My name is Siobhan Richards. I'm a mechanical engineer slash computer scientist. I've been a front-end engineer for 2 years, and I've taught computer science concepts as a professor for about a year. And this slide I have here will teach you the foundation of programming, the basics, right? Where did it all start? What's the IDE? What's a programming language? What are the best conventions to use when programming, right? So this slide here, you can see intro to programming using Python. So let's dive in, right? So first we have to discuss the history of computers, right? So what's the background of computers? We know now we have smartphones, we have laptops, desktops, and so on. But where did it all come from? Where did all this concept came from, right? So we have to do a quick deep dive into computer architecture, right? So this here is the von Neumann machine, right? So the von Neumann machine takes in some input, does some processing, and then we get some output. But the good thing about the von Neumann machine is that we have this memory component where we could store stuff inside, right? And then retrieve it later. And this is the foundation of pretty much all computing device, right? We have to gather some user input, do some processing, store it somewhere. Later we retrieve it, do more processing if necessary, and then we provide some output which matches our business logic. All right, so this is the von Neumann machine. But here is the hardware diagram shown of the von Neumann machine, right? So this logic, the logical diagram here, is broken down to these logical components. So what is memory? Memory is typically cache or hard disk, so you write these different bits to some rotating disk or some electrical component to store these bits that you could gather later on. And the CPU is the control unit as well as the logic unit. What are those? The control unit handles the orchestration of these processes, while the logic unit carries out the arithmetic. So just remember, a computer device is typically digital, right? So it'll take maybe analog or even digital signals, and then it'll do some arithmetic massaging of the bits or the data that comes in to store in memory whatever the output of that processing is, right? So that's von Neumann machine. But this was a pivotal moment because before von Neumann, we had single purpose computers, right? So these are computers designed for just one specific purpose. What is an example of a single purpose computer? A calculator, right? So if you have a calculator right now, you'll have these buttons that are built for this computer. You hit these buttons like one, zeros, two. You carry out some operation plus, and then it displays the answer on the screen, the LED screen that it has. Right, so that's like a single purpose. You can only do calculations on a calculator, right? Whatever functionalities that are built inside the calculator, that's all you can do. A general purpose computer is like your laptop. What do I mean? Your laptop has many different applications. You could have an application for word processing. You could have an application for video editing, which I'm using right now. You could have an application for browsing the internet, right, which is a collection of devices on one single network. All right, so what's the von Neumann machine? What did it do? We have these four major components, right? We have our CPU, arithmetic logic unit, control unit, which makes up your CPU. You have your memory, which stores data, and you have your output. So before the von Neumann machine, again, we only have single purpose, but the von Neumann machine or the von Neumann architecture allows us today to separate software from hardware. So instead of building a device specifically for browsing the internet, we just have the hardware, the underlying hardware on your computer, and then all these different applications could run on top of the same hardware. So so basically you're saving development, right? You're saving resources because you could have multiple applications on one device, and that's your laptop, desktop. That's a general purpose versus special purpose computer. And I hope that makes some sense here. Okay, so this separation from hardware and software allows us to have two paradigm in computing, right? So if you're an electrical engineer, typically you do hardware, right? So mainly VLSIs, chip design, and so on, and then software, which is what we're working towards, right? You getting to learn to program. We work on the application side. Basically, we create apps, right, to run on top of this hardware structure. So, what is the software for a computer? Basically, it's the code, right? If you ever heard of code, that's what a software is. It's a bunch of code, right? So, what do I mean? You have these files that has some operations, right? And this operation is transformed by another program, another file known as a compiler program, right? Or interpreter, depending on the language. Here is Python. So it's an interpreter that is used to break down whatever operations you have inside the file to machine code, which then breaks down to give signals to the hardware side of the computer, right, of the computing device. All right, so basically in Python, let's say you create a file which says print hello world. The print here is a function. So you would create a file called hello.py, which is a source code file, and then you run that source code. You'd say Python hello.py, and then it'll break it down, right? The compiler or interpreter to source code sends it to the underlying hardware, and then eventually you'll see your computer prints to you as a user the output hello world, right? So that's what's really going on here. And if we should dive just a little deeper so we have complete understanding of what's going on, we could look at the computer hardware and know that these are electrical engineering concepts, right? So if you've ever heard of combinational and sequential logic, these are all the different components. It's very small, right? These are nanoscale combinational sequential circuitry that are used to carry out the logic inside your hardware, right? So chip design, um, PCBs, and so on. Okay. All right. So what is programming? Basically, as a programmer, you're writing code, right? So in a given language or multiple language, you write code to provide some desired output, right? So the code is written to manipulate the computer's behavior, right, for some intended use, right? So what constitutes well-written code, right? So if you ever heard of clean coding, maybe not because it's your first time, but these are a good foundation to know, right? So Python uses snake case, and what is clean code? We have readable, understandable code. So in coding, you have variables and you have functions, right? And these have different names. So your variable names and function names should be meaningful, right? And you should follow consistent formatting. So indentation, spacing, how you structure your sequence of tokens, right? How you structure your language inside your source code. Okay, it should be modular, right? So you should have a module for each step inside the problem statement or your user story, right? So if you let's say you need code to gather user input, that should be one module, right? You could use that as one module. And then you need another piece of code to print output. You could create a module called display module, right? So should be modular, organized, right? So easy classes we'll look at later. So class responsibility. It should have meaningful names. Do not repeat yourself. Minimal complexity, well tested, easily extended. And we'll look a little on version control, which is like Git repository and perforce and so on. And it should follow solid principles. The other thing we need to know to build our foundation before even starting to code is this idea of lifecycle methods, right? Because this is what you will be doing in the real world, right? So lifecycle methods, what are these? Basically, if you've taken a business class before, or maybe not, these are life cycle methods. Basically, it's a way to show the life cycle of a product or a business, right? So we've taken those life cycle examples and we apply it to software engineering. So these two methods that we follow for the software development lifecycle is waterfall versus agile software engineering. So what is agile? Basically, we'll plan, define, design, test, and deploy our software. And we'll do that in a iterative process. So it's like a feedback loop, right? So why do we use agile, right? So maybe we don't have all the details of our design yet, but we could deploy something, get some user feedback because maybe users make some suggestion, right? And we see how it function in the real world. And then based on those suggestions, we improve that product and we keep doing this loop, making our software better and better as the days go by. The other way is waterfall. Basically, we get the requirements first before we get all the requirements first. And then the next step, we do our design, make sure all the designs are done, meaning the class diagrams, UMLs, and so on. The next step is implementation. We implement the software, we test, and we maintain. So it's no loops, it's a linear process. And there are cases where waterfall is better than agile, but the main approach used in software development is agile. So you will hear, I'm an agile software developer, right? That's usually some adjective used to describe the software development process. But the cases where waterfall will outperform is safety cases, right? So there are some software that you don't want to put into the market to get feedback from, like so safety critical software where you deploy it and trying to get feedback from it. That's a bad approach, right? It can't be an agile development. You want to make sure it works first before put it into the before deploying, so that individuals don't get hurt. Okay, so these are the two main approaches for software development. And again, this is not programming, but it's the overall umbrella which you're going to work under. Okay. All right. So you just decide, okay, I'm going to start programming. What are the tools needed, right? So these are called development tools. So you need some development tools. The first tool and the most important one is your integrated development environment. And this is called the IDE, right? So your IDE is your integrated development environment, and it's the main space that you use to write source code. So if you have like Android, they have Android Studio, Java, IntelliJ, you have Sublime, and these are basically editors. So similarly, where you use Word documents to write your Word documents, these are basically editors built to write programming languages, right? Write the different syntax that you need and logic you need to carry out the different operations. So that's your IDE, right? So some of these IDEs, they have different plugins, extensions, and all the different goodies that makes your development faster, right? So you're trying to be better, faster, quicker, right? Like with your development, right? The other thing that you need is a scripting language, right? So what is a scripting language, right? So remember, in computing, you have application software as well as system software. So remember a while back we talked about the von Neumann machine. Basically, you have a system software, which is your operating system that lies right on top of that von Neumann machine, on top of the hardware layer. And then your application may sometimes need to talk to the system to carry out some operations efficiently. To talk to your system, it's typically done via the kernel. And to get to the kernel, you need this scripting. You need some shell or some shell or command line, and you need these scripting languages to carry out these uh, system operations. I hope that makes sense. So you have your application software here, you have your system software over here, and then the application may sometimes need to talk to your system, and that is done via the shell. Okay, so what are common operating system um, um, commands? Sometimes you may need to make files, you need to destroy processes, you need to kill processes, you need to start a process, you may need to start another shell somewhere, right? So these are normally system level commands, right? So you want to learn a little on scripting language. We'll cover some of that with the Git bash. So this is the Git born again shell. Uh, and we use this Git bash here also for repository where we could save our code and track our processes that we have. And then again, another advantage of using the shell is that, for example, when you create a file, you use your mouse, you click create new folder, new file. That's kind of slow versus when you're on the command line, you have direct access to your system, so you could just type a quick command and it creates the file very fast. So in terms of efficiency, using the command line makes development quicker. Okay, so that's why we need to know some scripting language now or later on. But for this class, we'll just cover basics because you've never written a line of code before, and these are just again general foundational stuff that you need to know before even writing a line of code, so that you understand clearly what you're doing as a developer. Okay, so our main IDE that we'll use here is the Visual Studio Code, right? And again, these IDEs makes development easier, and it's a rich ecosystem for many languages, not just Python, C++, Java, JavaScript. You could use the VS Code IDE for that as well. Okay, so getting started with Python. So you've chosen Python as your first language, and you've decided, okay, I need to learn Python. Okay, all right, so we have this link here to get you started, but let's just cover some stuff first, and then we'll use a online compiler or online Python interpreter to write our first lines of Python code. Okay, so just a little more here. Okay, so Python is a programming language that lets you work more quickly, right? And you could integrate your system commands more efficiently with Python. It's a scripting, kind of like a scripting language, programming language hybrid in a sense, right? So it's simple, straightforward syntax to do complex work, right? So generally, when you're programming, you'll hear of these two main type of errors that you may face, and they are syntax errors as well as semantic errors, right? So syntax is typically the structure of your code. So are you following these rules, right? Structural rules of your code, right? And just remember, this is language. So for example, are you following the subject verb agreement in English, right? So like, in Python, are you following, can this token come after this token here, or reserve word? So that's the structural. And this is not really the main cause of a lot of programming issues. Usually you could solve these syntax errors via a linting tool. So if you have some linting tool involved in your development, syntax errors won't be a problem. The errors that will be a problem are semantic errors. Are you getting the meaning, right? So these are the meaning and interpretation of the language. Are you understanding the underlying meaning of the language, the Python language itself? Okay, so these are harder to catch. Why are semantic errors harder to catch? Because your code might run, right? So your code might run, but the output that was intended is incorrect. So that's usually where you have to do a lot of debugging, which is a main skill needed uh, to develop software rapidly. Okay, so our first topic here is reserved words, right? So what are reserved words? These are words that are stored in the programming language that you can't use as variable names, right? So these are set aside in the programming language and you can't use those as any variables or function names, right? Because you may do an overwrite and you don't want to do that. So never use keywords, reserved keywords as variable names. That's the first thing that you need to know. Okay, so we could see here we have false, true, none, and, as, assert, break, class, continue. We have a lot of reserved words. You don't need to study them. Usually in your language, you'll see some highlight, right? So for Python, maybe the reserved words, they turn blue to show you that it's a reserved word in the language in your IDE. Okay, so you can't use these words as identifiers such as variable names, function names, class names, or labels because they are already predefined in the language. Okay, and then the next thing that we need to know before we write our first line of code is the use of indentation, so or scope. So what is scope? Scope tells us what operations are tied to what function, or how other function or how other parts of the code access certain variables. So that's kind of more clearer. So scope shows us how do other things access this part of the code, right? So usually it's used in functions, right? So you scope your functions, right? And we'll discuss functions later. But basically in Python, if you see indentation over, that shows you that those lines follow that function header. So that's kind of the main concept here. Okay, the next thing that we'll discuss and we'll start coding, write our first couple lines of code here, is data types in Python. And just to note, Python is a dynamically typed language. And what does that mean? It means that these data types that I'm going to mention here you don't have to explicitly tell the IDE this is an integer, right? Or this is a text, or this is a sequence. Python will figure it out on its own based on what you store inside of that variable name, right? So it'll figure it out on its own based on what is stored. So these are the main data types in Python. You have a text type. These are categories, numeric types, sequence types, mapping types, set types, Boolean types, binary types, and none types. So the text type, under the text type, you have string. For the numeric type, you have ints, floats, complex. Sequence types, you have list, tuple, range. Mapping types, you have dicts, which are dictionaries. Set types, you have set, frozen set. Boolean types, you have bools. Binary types, you have bytes, byte arrays, memory view. And none types, you have the none type. Okay, so these are all the types that you're going to come across when you're coding in Python. This is very important when you're starting to code in Python. So these are all the main types that you're going to come across. Okay, so what are built-in data types? Right, these involve handling, storing, and processing data, right, for some desired output. I just want you to just remember the von Neumann machine, and you'll see that most of the times when you're programming or you're writing, whether it's programming, software, hardware, it will resort to the concept of the von Neumann machine. In my opinion, I think programming is really rewriting the von Neumann machine over and over and over again. I know it's the underlying structure of the computer, and all these abstraction is the von Neumann machine being repeated over and over again. It's always gathering user input, doing some processing, and then getting output. That's the structure, and that's the structure of the underlying hardware, and that's the structure of the uh, application software as well. All right, so just remember these are the data types. The next step is the next video I'll go into creating these data types. So how do we create it? Okay, and then we'll come back to the slides the other video. Okay. All right. Thank you for listening, and I hope I'm making some impact here. Thank you.